You do this one time, like the day before you invite people to the station. And you can go, oh.
Yeah, I've done that once, and then when I came up. There was no parking, so what? The day I came, because usually I can park in the F space, but sometimes it's not, there's still C left, same floor. So you can just go and just see, that's $3. Oh, okay.
But you have to pay across in the parking garage. The machine.
No, it's all done online with the online. So you guys get it. The process is cumbersome. Yeah, I just do it on the spot. Oh, yeah, because, yeah.
And then you would only wait until like 5 hours.
Whatever, sometimes we wait a few minutes, sometimes we just get started. I
Okay,
don't think there's a convention, so to speak.
okay, well, let's just wait a few minutes. So we have this thing called Berkeley time, which I think you know about. Where classes start about 10 minutes after the actual hour.
Yeah, we have 15 minutes, and we have the same problem, we have something short, but then it's, oh, people turn up 15 minutes later.
Right, right.
The see in Sweden, they have 5 minutes.
It's 5 minutes.
Yeah. So
They
instead
also
of meeting
get-
with them, that's short, they have 5 minutes late. But you have to 15 minutes late. It's. And you're on time.
It's kind of during the pandemic when everyone started to do Outlook meetings, then I thought a bit strange, then I wrote meetings short. So nowadays it's less frequent, it's only almost a teacher that uses this academic quarter.
So some folks who joining us online.
So that's also the city where the university is, Linköping.
Yes, so this is actually Norrköping, which is kind of 40 kilometers closer to Stockholm.
I see.
So the picture is from Norrköping. So it's really nice.
Yes, nice.
And the campus of Linköping, which is larger, is it's not so nice. for photos. Yeah.
It's by the sea.
Yeah, Norrköping is by the sea, yes. So even if we don't see the ocean from the campus, we have this stream.
Yeah.
That kind of passes by just outside the university buildings.
That means it's warmer than the rest part of Sweden.
Yeah, maybe.
Maybe.
Here and there. When it's snow in Linköping, when I arrived in Norrköping, it can be no snow. But it's, no, usually it's kind of follows the same, so it has, no.
Yeah, I know it must be really hard during the winter, like really low temperature and. Compared to here, yes.
Yeah, some mornings are tougher than other mornings. But I think the darkness is kind of worse.
So let me guess, you never lived in a place with there's snow?
No, the north place I live in is Cincinnati. It's like
Okay, well, still, so.
20 Celsius degree lower than.
I grew up in Ottawa in Canada, so.
But snow is nice, I mean,
It's
it's
nice.
now, when we don't have any snow, it's kind of dark and gloomy and, but as soon as the snow comes, it's all lightens up again.
Oh, yeah.
Yeah, you can go out without getting wet.
Exactly, yeah.
But then it's good through the holidays, but usually in my case, whenever you hit mid-January, then yeah, that's quite enough. Until you spend a month like at minus 15°C and it's 20°C, so yeah, now it's time for spring.
Exactly, and then still until April before it's gone.
Yeah, well, it's about 5 after, I think this is a good time to start. So, today it's my pleasure to introduce our speakers at today's PATH seminar. Thank you, everyone, for joining. Our guests come all the way from Linköping University in Sweden, and they have a lab group that specializes in transport analytics, and they're going to tell us about their work today. So I'd like to introduce Professor Claes Rydergren, Professor David Bimmelgaard, and soon to be Dr. Anna Danielsson. So thank you very much. Please take it away.
Thank you. So yeah, we have a title, Large Scale Mobility Data for Management of Transport Networks. So it will be related to modeling, but we will focus most on how we process data and get insights on what's going on in the transportation system and how we can maybe even manage that. That's the topic of the seminar. So you have already introduced Linköping University. It's kind of the fifth largest university in Sweden, and maybe the fifth oldest university as well, 50 years old next year. And it kind of covers everything. But we are part of the Faculty of Science and Engineering, or sometimes we call ourselves Institute of Technology as well. But we also have medicine and art and science and education and stuff. Kind of 30,000 students and about 4,000 staff members. So it's, I don't know how it compares to Berkeley, but yeah, around this in Sweden. And the three of us are all from the same division. It's called Communication and Transport Systems. And we are about 80 employees, some seniors, and about 1/4 is PhD students, and also then just teachers and research engineers. So what we do is not only research, but also connected to the responsibility and undergraduate education, on top of the graduate education then. So we have a number of programs that we are more or less in charge of. So in Sweden, there are master programs that are 5 years, where you start out on a track of 5 years, and we are responsible for one of those. And then we also have master programs that are 2 years, which is only the last years. And they are related to transport and logistics. So some more focus on logistics, but our largest program is the one that focuses on transport, which also have this transport system and logistics, where David is in charge, which is kind of an international copy of the Swedish program, even if it's only the last 2 years. So the transport analytics group is where we do investigation on this large scale mobility data. So we have a number of applications where we do this. So kind of overall estimation of multimodal traffic flows, either for energy focused transport planning, or for highway traffic management, or highway incident detection, is typical applications that we can talk about. We will focus on some of them later on, but we also have research in bicycle simulation, and also related to emission and energy consumption. So looking at the communication and transport division, there are a number of research areas outside of the transport analytics. So we have a history coming from a combination of telecommunications and traffic modeling, and also now logistics. You can see the specializations, but we will mainly focus on the one that we call transport analytics. And in this group, we work with a lot of applications, but what they have in common is the large-scale mobility data. And the examples of large-scale mobility data, something that you're already familiar with, GPS trip data or GPS trajectories, public transport ticket data. Stockholm have 2 toll systems in Stockholm and Göteborg, and they also provide some data. So there's the toll portal data, and that is not only the number of passengers, but also register which vehicle and which type of vehicle and so on. And you can also see who owns that vehicle. So and more traditional data of link counts. And we have also worked quite a lot with mobile network data that kind of comes from the mobile phone operators. So in Sweden, there is one major operator that have about 50% of the market. So they are able to share, at least for research purposes, data on mobility. So these types of large-scale mobility data is what we use in our, what we can call applications or projects. And one of the projects is data-driven network design. And David will speak about that one.
Yes. So Claes mentioned a few different types of projects, and we will kind of speak a little bit more about two different topics. One is this, the data-driven network assignment, and the other one is called multimodal traffic management, which is Anna will talk a little bit about in the end. But this work, well, the background to it started maybe 15 years ago when we started to work a lot with the mobile network data or cellular network data to understand mobility patterns. And we got quite good. One of the interesting things with mobile network data is that you can get sampled observations of travel demand, which was kind of hard to get before that. And that put us in a situation where we kind of, okay, we have some kind of OD in an area, but how do we assign it to the network? And then we worked with a number of cities where we didn't have any model that we could use to assign the ODs. And as you know, we've been working with Connected Corridors model in Los Angeles, so it's very complex to calibrate these kind of models. And we had a similar thing in Stockholm, for example, where we didn't have the resources to kind of have a calibrated model for that area. We also worked in examples in Africa, Dakar, where we had no clue about how does this city work. So then we thought about, could we assign this travel demand onto the road network in a different way? And then with having more data available, we could maybe see if we can get measurements of observations of how you choose the routes and how vehicles are propagated in the network. And we started off with this, trying to use the inherent data available in the cellular networks to determine the routes, and then in that way also get link flows out of these travel demands. And we did some work on that, trying to find algorithms for determining routes based on this noisy cellular network data that we had available. But then we realized a few years later there was a lot of data, or the penetration rate of GPS Pro vehicles became much larger. So we will get more of the vehicles that have GPS devices in them, which we can follow in much higher resolution in both space and time. So then we thought about, okay, why don't we try to utilize that data for doing the assignment, and then we can use the OD from the mobile network data as input to that. And then we started with this, that was the more specific part of this data-driven network assignment. So the difference with that is that we usually have some kind of link flows Y that we might be interested in, and we have some OD matrix S, X, and then we assign X onto the road network in order to get the link flows Y. The problem with the equilibrium-based models is that the assignment function depends on the ODs, or the demand, which makes this function a little bit complicated. So what we thought that we could do is that have exogenous data in terms of measurements of travel times and route choice. We call it SED here. And then we can create this assignment function that doesn't depend on X. And the early work on this, we spent many years actually just discussing this. Is this relevant? Is it interesting to have this assignment where you have travel times as input? So this is the whole difference, right? normally the travel times are output of the equilibrium process. And then we discussed with many people that were in the field, and I mean, that doesn't make sense. Why would we want to do that? And we kind of also, but it could be cases where we this could be interesting. So we kept on working with that, and we had a PhD student working on this for a few years. Figure out the first part, which is the network loading part. For instance, this is also published in one of the papers called Data-Driven Network Loading a few years ago. And then the work he did was mostly to kind of get all the details of how we find this assignment function A here by looking at the two matrices Q and R, where Q is how we use measurements from GPS probe data to do the network loading, and then also use GPS probe data to get the route choice matrix. And then we have a setup where we can multiply this loading matrix with the route choice matrix in order to get this assignment matrix. So we, for example, see how we can use GPS probe data to determine the route flows from one origin to another origin here. And this is an example of how we looked at or compared the propagation or the loading part of the model in a simulator. So we worked a lot in simulated environments here. So this was the concept of data-driven network assignments. And then we thought about, well, what can we use this for? Yes.
So what are the dimensions of these matrices, Q and R?
Yeah, Q. So the A matrix, the assignment matrix, that maps the demand onto the link flows for specific time periods, right? But then Q here, that maps principally route choices or routes onto link flows for specific time intervals. And R maps the OD entries to routes. And the assignment matrix then tells us how large proportion of the OD flow that we have in a certain OD pair is traversing a certain link at a certain time, depending on when it started, right? So that's what this assignment matrix includes. So it's a value between 0 and 1 in all the entries. And this becomes relatively large in many cases. And we'll look at some examples of that.
Can you always find a solution for your assignment?
Yeah, I mean, what we're doing is that we measure the travel times, for example, and of course we estimate it, I would say. So of course it's not the A matrix is not accurate, but it's using measurements as input. So it's the best thing that we know at that specific point in time. So I might also add some limitation of this. So what does this mean? The fact that we're using measurements as input when we're making the assignment matrix. Well, it means that we cannot use it for situations where we don't have the supply, right? So if we want to model things like, say that we change, we add the link or we remove a link in the network, then we cannot use this support. So this is purely about understanding how does the demand, how is the demand assigned to the network, and when we have measurements for it. So that is one important limitation that should not be, confused when we look at this kind of assignment matrices. So the question was now, what will we use this for? Well, one of the things that we realized that this was useful for was for estimating OD. So estimating OD is challenging also in real time, right? So not only predicting OD, but also doing it in real time or doing it even historically is challenging. So that's where we realized that, yeah, if we have a mapping between OD and link flows that can be calculated relatively easy. It's not so easy, we realized after a few years, but still, once we have made this assignment function that takes the measurements as input, we have a linear mapping between the OD flows and the link flows, which is going to make the this translation from OD to link flows relatively fast, which means that we can also change from this kind of target function when estimating the OD, where the assignment depends on X. Then you have to make this iterative approach or bi-level optimization approach. So instead we can use this function and get the results directly when we have the measurements. So what we do is that we have the OD flows, we assign it onto the network, compare it with or get the link flows, compare that to the link counts, and then adjust the OD flows like that. And then we try this and to see how it works in a simulated environment. So you might recognize that network.
Oh yeah.
So that is together with Anthony. We kind of used the AIMSUN simulated network in Los Angeles for the connected corridors network. And try to see how it works for doing all the estimation on that. We also tried the more simple network just to see how it behaves. We realized that we have to do things very simple in the beginning to see how does it work. And that was a relatively complex network from what we tried before, but it worked quite well for that network as well. So we can see some examples of estimated and predicted link flows, the correlation between them when we have other types of traditional assignment methods with our data-driven approach. And it worked reasonably well, but of course, when we have a simulated environment, we know what kind of assumptions are made in the model, which makes it easy, relatively easy. But that was kind of the precondition that it works for controlled conditions. And this is also published in this paper on all the matrix estimation based on data-driven network assignment, still in simulated environments. And then we have started to think about, well, can we apply this in real networks and see how we can use it with real data? So for some stupid reason, we started up with the left network here in Stockholm with 350,000 OD pairs. I thought that this is probably fine, but it was very, very challenging. So we came to simpler networks. And I mean, in the beginning, we had all networks without root choice, for example, just to see how it works. But now we're working with these kind of networks with a few thousand OD pairs. We can have an idea how it works. And we're actually getting some results on that larger networks as well. And this is the city of Norrköping, which we're also working a lot. I will show some examples of that later. But also for this larger network, we had the red dots that you hardly can see there, or where we have link counts. And then input to this was also that we had an OD matrix from the DOT in Sweden about approximate OD matrix. And then we adjusted it using this data-driven network assignment using GPS probe data as input for root choice and travel times. And we can see that when we compare the design flows for the original model and our model, it was improved. And not only for the sensors that we used for estimating the OD, but also on the sensors that were not used in the estimation of the OD matrix. So this is for the training sensors, the ones that were used for estimating the OD. These were sensors that were not used when estimating the OD matrix. So it has, of course, it's an undetermined or overdetermined problem. So undetermined problem, so we can adapt the OD quite a lot. But also for the sensors that we didn't see in the estimation, it worked quite well. And even for this large network, we were able to do something at least. And this right-hand picture here is when we assign the link flows onto the networks, it looks like that, and it doesn't look completely strange at least. And then we also continue to get more experiments with the smaller networks to see how it behaves under different conditions. how much weight should we put on the structure of the data from the historical OD, and how much should we put on the sensor data that we add in terms of the link counts. And also here we have the correlation between the predicted and true link counts on the training sensors that we use for estimating the OD and the ones that were not seen. And it looks reasonable as well. We have okay results, and we can see that how much we weight the historical data is quite important also for not overfitting the OD matrix in this case. I stop there, and Claes will continue about OD matrices from public transport.
Yes, so since many of the applications that we have are kind of multimodal in the sense that we don't only like to do the analysis of cars, but we like to do transports in general. And for most of the Swedish cities, public transport is relatively well used. So it makes sense to try to also construct information on the OD for public transport. And this will be a much shorter presentation because the data is so much better. So there are these GTFS timetable data, kind of presenting the supply, making the network much simpler to work with, but there are also systems that more or less provides the OD information already. So a typical public transport operator in Sweden collect and store those type of ticket validations and also have in-vehicle counters. So you typically have automatic fare collection, meaning that in Sweden you tap your card when you enter the vehicle and then nothing more. But still, you tap it when you enter. It's connected to which vehicle and which type of card and your ID. And the automatic passenger count data is completely anonymous, but it counts the number of people that enters a vehicle at a certain time and also how many that exits. So you can see if I stop, how many enters the vehicle, how many that exits the vehicle. Yes.
Just one question, when we're talking OD here, you're talking about from entering the public transport vehicle to leaving the public transport vehicle, so it's not really the passenger's origin and destination.
Exactly.
Oh, okay.
Yeah. So there is, even if this is kind of good data, and if these were kind of perfect, then we have a stop-by-stop OD matrix. But we don't have a home-to-work OD matrix in that sense.
Yeah,
so there is still an estimation part, which I will not talk about, how we map the stops to the actual traffic analysis zones, which we used directly when we did the car-based OD assignment.
Okay.
And that's is still kind of a hand waving, kind of what is coverage areas of public transport stops and what type of connections do you make? Do you take the car to the public transport stop or not? But the most common thing in Sweden is that you either walk or take your bike to the bus stop. So the distance is relatively short. So it should be but it's still an approximation. And we really don't know. But compared to car OD, it's simpler to do public transport OD. So we can, even if there is only this tap in information, we can use that to estimate what the trip will be. So if you tap in twice, you get some information of where you typically alighted the vehicle. And we can use that as an estimate for both boarding and alighting. And so that will provide some type of estimates. And there has been a lot of publications on that. So we just used one more or less off-the-shelf algorithm for going from only tap in to OD on stop-by-stop basis. And then we combine that with this vehicle counting data. That's how many that enters and how many that exits. So you can, even if the people are a bit sloppy, they don't tap in always, and some try to cheat, then so the data is not completely accurate, and also that there is an estimation process of what was your actual destination stop that was inferred by this algorithm. We use the boarding and the alighting count to rescale or rebalance this matrix, and the output from that would then be a relatively good estimate of what the demand look like for public transport on a stop-by-stop basis. And then there's this process of going from stop to traffic analysis zones. So that means that we now have two OD estimation processes, one for cars and one for public transport. We still are lacking one for bikes and walk. I guess that we will come to them soon as well. But with only these two, we have a lot of applications where we like to sell procedures or provide results to stakeholders based on these two. And they will start with one of them.
Yes.
And then I will do something, and then Anna will present the last one.
So the first project here is called CodeFlow. It's one of the projects that kind of utilize this data-driven network assignment to see what we can do with it. And what we wanted to do in this project was to kind of see what if we can estimate OD, link flows, route flows continuously over time. So 24/7 during full years. What can we use that for? So we discussed with the DOT, for example, in Sweden to see about the other really interested in before-after studies. So what happens when you make a change to the infrastructure, for example, to monitor that and be able to see that in practice. There's a lot of modeling typically before you make an investment in infrastructure, but the following up afterwards is not always that accurate or good. At least in Sweden. So with this, we can, if we have a system that monitors this more continuously, we can do more of these follow-ups to see how what kind of effect these investments have. We could potentially do also more agile traffic planning to see what are our actions, how they affect the traffic systems. But importantly, it can also be input to new models, right? So if we understand how the OD, link flows and route flows varies over time, we can try to connect that to different things that will affect the travel patterns. So that is also one idea to motivate doing this continuously over time. So what we do? Well, in this case, we use mobile network data as input target matrix. Then we have GPS probe data for route choice and propagation of the vehicles. And then we have the link flows that we have measurements of for scaling the OD matrix. And what we're trying to build is some kind of automated and scalable process for large networks and long time periods. So it's not automated yet. It doesn't handle that large networks yet. But this is just an example where the red lines here indicate the OD flows and the black lines indicate the link flows. And we're doing this for 24 hours here in the Norrköping network, just to see how the OD and link flows vary over time of day. And then it is, of course, to make this over several years so that we can understand travel patterns or mobility patterns in terms of link flows and OD flows. And specifically for the municipality here, they have this 24-hour model that they wanted to shift to a time-sliced OD matrix instead. So this could be used potentially as input for that.
Yeah, and another application. So typically when you do long-term planning, you have some of the more traditional targets. You like to have a good throughput and you like to provide good accessibility and so on. But there is also maybe an interest on energy use, especially if we go from fossil fuel to electrified vehicles. And there will be an effect of that, but there is also an effect on the energy use from the planning aspect. So if we have an OD description for private cars and an OD description for public transport, the idea with this energy-focused transport planning was to kind of identify traveler relations where public transport is competitive, meaning that here it makes sense to offer public transport. We might also identify other traveler relations where public transport is not offered right now, but has a potential to be. And of course, we can also have the other way around. We offer a lot of public transport, but no one is using it because the car is just as energy efficient. And that would be a use of our combined OD mapping on private cars and public transport. So the idea was to combine this data-driven network assignment process and the OD estimation based on that and the public transport OD estimation, and look at situations where public transport is competitive with car. And to do that, we need to have some type of energy model. So Europe have a number of standardized energy models. That's one called HB5, where Sweden invests a bit in updating and provide with an estimate of what the development of the vehicle fleet is on a national level. So, and that is kind of input to this model. And if you provide the model with a typical traffic state, meaning that how fast or what the congestion level you have and the travel distance, then this energy model will then provide the energy use for you. So it makes sense that if we know the demand and also know which routes are used, at least for a car, it would be easy to get the total energy used for that trip. And we can do the same, or at least similar, for buses. The problem with buses is, or the benefit with buses is that you share the same vehicle. So it's hard to allocate what is the energy used for traveler A when you're sharing that vehicle with several other travelers. But if we have some simple way of just allocating the bus energy use down to travelers, kind of in an equal share way. So if there are more travelers on the bus, when you use it, your energy consumption or energy use is lower when if you travel on the bus on your own. So
do you know what the rough mode share in Sweden is? Just curious.
It's super different for different areas, but I think we are over 50% in Stockholm, but I think that we are lower than 30% in the Linköping, Norrköping area. And outside of that, I would say public transport may not even exist. And it might be this demand responsive, so super low.
Yeah, cool. Thanks.
So, and then not cars, I would say, yeah.
When you're allocating the bus energy use to passengers, you're looking at the incremental energy use per passenger or the average? Because it would make a huge difference.
I would guess that I will answer average, but what do you mean by incremental?
Incremental, if the bus has 30 passengers and I'm now the 31st passenger, how much more energy does the bus use because I'm on the bus?
Oh, okay, no, not the incremental, no.
Okay.
No. So definitely the average.
Average.
Yeah.
Okay.
Yes. So in order to do this allocation, we need to know number of buses per link and travelers then per link, meaning that on the buses and the link state and the OD demand. Then we can do this down to individuals. How would they contribute to the energy use, or which share of the energy use should you allocate on each of the travelers? And that is exactly the input data that we get from both for cars, for the OD matrix, and for the analysis of the public transport data for the OD data for public transport. And with doing that, and with the use of the energy model, we can kind of if we look at a certain origin destination relation, then we can look at what is the trade-off. So depending on how many users we have along a line, we can identify travel relations where public transport is more efficient or less efficient. So obviously, if we have a higher demand, the public transport will be more efficient, but it doesn't have to be in the exact this origin destination pair. It could also be travelers traveling a longer distance. So if you board a bus that is almost already full, then that will be super beneficial for you, since your energy use will be lower. And then we get this kind of trade-off curve. So the black line would be, here is the energy use for car, which is typically 1.2 travelers per car. And we can compare that with the green curve, which kind of, we see that the more travelers that we can allocate to a bus line, the more efficient the bus line will be. So that is kind of an energy use application. We also have a traffic work application, then we are down to the road network again.
Yeah, and we mainly mentioned this because you mentioned vehicle miles travel, that you're working with that. And we also have one application of this is when we make the OD estimation and the route choices, we can also try to estimate the vehicle miles travel from that directly, or just compute it if that would be accurate. So in our case, what we're doing is to try to compare it. So the DOT is really interested in how to utilize large-scale mobility data for understanding vehicle miles traveled. And so what we started with was to kind of compare it with the traditional methods. So this is an ongoing project, so don't have all the results yet, but we started on a simple, the major roads, the red ones, and orange ones in this graph, in this plot over here. We looked at the vehicle miles traveled from GPS probe data, simple scaling approach. Of course, we can also use the mobile network data to assign the OD to the route choice to get the vehicle miles traveled. Here we just used the simplified approach where we just scale the penetration rates of probe vehicles and to see what we get in terms of vehicle miles traveled, and compare that with the regular methods, which include travel surveys and also this reporting of annual miles traveled or kilometers traveled for each vehicle in Sweden. And then we did it so this is for 15 years. What was the average vehicle miles traveled in this network per day? On average per day for 15 years. And this was for 5 weeks. So what kind of vehicle miles travel per day did we have based on probe data? So this is just the first kind of comparison with this, and of course, it doesn't look completely stupid, at least. But the question is, of course, can we utilize this kind of data to make this high resolution so we can measure maybe the daily level or weekly level of this vehicle miles travel for a larger network or the entire country? I stop here. We can talk more about this vehicle miles travel later.
Yes, the next project is multimodal traffic management, which is where I spend most of my time. And by multimodal, we mean the simultaneous management of road traffic and public transport in urban areas. And what we want to do is to better understand the multimodal travel patterns for road traffic on cars and public transport. And not only trips including both car and public transport, but also studying those two modes simultaneously. We want to find new methods for multimodal demand estimation and prediction, which includes predicting route and mode choice. And maybe most importantly, we want to find synergy effects of studying management of several modes together. The project also includes incident decision support and incident management, which means traffic state prediction for both typical days and during incidents. And this means, or interesting questions are like, what traveler flows are affected by a specific incident, and also what travelers affect the incident the most, which travelers are causing most of the congestion, and what other multimodal alternatives do these travelers have, and how would this rerouting affect future state of the traffic state. So we started off by looking for effects of multimodal traffic management in the literature. And synergies include easier shifts between different modes, both within the same trip and before the trip starts. Also, by utilizing the full potential of the network, there will be more degrees of freedoms for the traffic management centers. So it will be easier to prioritize between different management measures. There's also a synergy effect that easier information accessibility. Yeah.
I have a
Question?
question in Sweden, do you have a lot of like micromobility or like electric scooters or electric bikes? And do you look at how those have, you know, synergies with, I don't know, you know, bus or train?
There are scooters and micromobility and bikes in at least the larger cities. But we haven't looked into how that's included in the management centers. Those are not managed at the moment. Yeah, but the easier access to information for different modes can lead to more informed decisions, which is expected to lead to more environmental friendly travel behavior. Challenges include a collaboration between different authorities, and both economical, political, and social challenges, such as data standards and paying for common investments and competition between the customers. There is also a lack of prediction models to use as decision support for multimodal traffic management. And that includes also the integration of different data sources. And that leads us to our focus in this project, or our main focus, which is to develop these kind of prediction models. So the idea is to construct management strategies based on simulation model scenario analysis. And the focus is on reducing the congestion in the road traffic by shifting travelers to the public transport. And we want to understand how route and mode choice specifically are impacted by congestion. And specifically by incidents, how route and mode choice are affected by incidents, and what multimodal alternatives there are for the travelers that are affected or affecting the incident. Yes, that was a question.
So this is also a bit more qualitative, but I'm curious if you know, I guess how common are multimodal trips where the car is one component of the trip? And then second is, what are the incentives or the reasons that you've seen why people are choosing to make a trip, say, partly by private vehicle and partly by transit, or partly by private vehicle and bike, etc. And how is that fitting in?
Yeah, I don't know how common it is. Do you know?
Not very common, I would say.
I would imagine, yes,
Yeah.
so when we're talking about multimodal trips, are we more talking about, say, bike to transit type trips? What are the trips that we're talking about for multimodal trips?
No, so when we define the multimodal thing,
Or just try buying it holistic, okay.
so it's cars and public transport in the same system, but it doesn't have to be connected in the same trip.
Gotcha,
So when you plan for some incident,
Sure, I think so.
there is a shift
I
in
misheard.
windows
gotcha.
already from the order.
Yep,
So
yep.
there are other definitions of multimodal.
That's perfect, yeah, we're on the same page.
But it's a good point, because these, for example, parkings that you use when you travel into the city and then switch are not included in the kind of modeling you're thinking about right now, but that's an important part of the future, yes.
Yeah, that's something that needs to be added in the models. Yes.
I guess then still then with, that makes it simpler, I would still, I guess I'm curious, and I've seen this as occasionally a challenge, especially in some of the US models, is I'm curious how you were building in the cost differences for, like, what are the costs for driving a private vehicle? And in particular, what are you including beyond the congestion? So would there be, like parking fees, et cetera, like how is that difficulty included in your decision-making process?
That will be important questions when you start working more with the mode choice, right?
Yeah,
Yeah, it's just more choice questions, yeah.
But then, and I
Don't
think
have to
working
do that.
mostly on the root choice so far, but we're just about to start the more choice as well, and then it's will be important.
And we are still in the context of analyzing data more than trying to predict. So values of time and specific costs. Of course, they have an influence, but as soon as we have the measurements for them and also the measurements on how they have reacted to that.
Yes.
Yeah, that will.
So this is more of my personal bugaboo. I feel sometimes when folks are doing no choice, they don't appropriately account for parking costs / parking availability. And then they just end up having to do these, big fixes on the side.
Yeah.
Yeah, go ahead, please.
so yeah, up until now, the route choice has been the focus. And here's just an example of how a route choice can be affected by an incident. So we see the normal behavior to the left in an origin destination pair going from south to north. And here is how it looks like during the incident. So we see that during normal days, most people use the highway, and then the opposite of the incident day. More people use the alternative routes. Yes. That was all on the multimodal traffic management. And now for the last project, which is the project that brings us here, or like the main reason that we are here in California now, which is a collaboration with a startup in Los Angeles called Xtelligent. And together with them, we work on a dashboard to create or increase situational awareness for traffic management centers. So in this dashboard, we develop performance indicators for following the state of the network and where the congestions are and things like that, which is based on sensor data. There are also delay graphs or congestion graphs, both for the whole network and also for specific identified routes or corridors that are more interesting. There's also some anomaly detection in these delay graphs with alerts to notify if there's something that deviates from the normal variations. There are also alternative routes in this dashboard. So when the incident occurs, the traffic management center want to find alternative routes for the car users to get around the incident. And these alternative routes will typically be outside of the main highway on smaller roads, and there might need to be adjustments on those intersections and signalized intersections in particular. So maybe there needs to be some improvement in the schedules for those signal controls to increase the throughput now that there are maybe more flow, but also different kind of flow. So it's just an example of what the dashboard looked like, both the network state of the delay or the state of the network, specific routes and centered around incidents that are in the network. Yeah, I think I will stop there and open up for more questions. We already got some questions, but are there any other of the projects that we presented?
Maybe one broader question, since you're very dependent on the availability of data, how does the GDPR and all of the privacy concerns affect the availability of the data that you use as inputs for the analysis?
Yeah, it's affecting a lot, especially in terms of we're working a lot with the mobile network, with the cell network data, where you have strict limitations on what you can or what the operators share externally. So we have had, for example, projects where we, instead of having them sharing data with us, we share code with them. So they run code on their systems locally without us seeing anything.
Oh, so they don't even need to share the data with you?
No,
then?
exactly. So that's the kind of setups that we're working with related to that, and that's super complex and time consuming. But it's for the GPS data that we have a data set from Inrix, for example. We're also working with TomTom. They are surprising. I mean, TomTom have some limitations on how they aggregate data, but Inrix is surprisingly, raw data that we get. I'm not sure if that will continue, but it's challenging. Yes.
Yeah, because that's one of the challenges we face here, even though we don't have GDPR, there's still company concerns about data sharing that.
Yeah.
That's what we can do.
Yeah, and with GDPR, it's also the companies are much more, they are more eager to make sure that they follow the rules. So yeah, they don't want to take chances about sending data to researchers if they're not sure that it's okay.
I had a question about your first subject, the continuous OD estimation and workflows. What was the granularity of the OD matrices that you were looking at from the visual? It looked like it was hourly.
Yeah, just hourly.
But I was trying to get an idea of what sort of the ranges are for sort of a real-time application of this, what you're shooting for.
That's a good question. We have, I mean, the concept itself have the possibility to have any kind of resolution. So we thought about, seconds or minutes or and so on. But of course, the processing gets more complicated. But I think that for real time, we're having some thoughts about also estimating all the measures in real time for chat management applications. And then I think we are looking at 15-minute level. So prediction maybe next coming 15 minutes would be appropriate. That's what we're thinking at least. We haven't tried that yet. We still struggle with the 1 hour period.
Right, and then for that particular, those pictures that you showed, approximately how big was that network? Was that the big one that was at the 87K links?
If you go back, that one that we Norrköping network, you can have the slide with all the networks. There.
This one, right?
Yeah, exactly. So the middle one that we are working okay with now is the one with 37,000 links and 40,000 only birds.
And that was the one you were doing the hourly.
Yeah.
You were doing the hourly OD estimations based on whatever data you have. Is that correct?
Yeah.
And then how long does it? So okay, you want to do this in real time. So you get the data and then you have to process it. Like how long does that processing take?
So for now, we use a longer period with the GPS data.
Okay.
Kind of in several weeks, and produce an average in terms of the route choice information, so that we'll never be able to update in real time with this process that we have now.
I see. So what you were showing earlier, you have some history of data, and then you use that to create sort of an average day. I've got these hourly OD matrices that you can create. Okay.
So the route choice is more or less on average. But on the other hand, the link count data and the mobile network data is close to real time. So that is also a main input, at least to the OD estimation. So the idea is that we get an OD that is kind of accurate, down to an hour at least. But sure, if there are incidents and differences in route choices, then we will be off.
But I think it's important. I mean, we're one of the things that we're thinking about doing now is to be able to run real-time estimation and short-term prediction on the left network there. And of course, it's challenging, but with other dimensional action methods on OD works quite well. Typically, can help. But the bottleneck we have right now is to create this assignment matrix for hour by hour. That takes a long time as it is now, but. So we need to make it more efficient on estimating this assignment matrix in order to be able to run it in real time. But maybe we do it then cluster these assignment matrices, finding that okay, for this type of days we have this type of assignment matrices. There are challenges related to that, but I don't think it's impossible.
And I think that also monitoring it hour by hour for many years, that will help you to also get better data driven or better inputs to models for how to predict, for example, in the coming hour. And the idea that making this hour by hour, 50 minutes by 50 minutes for years, then we will also have a better input for making predictions.
Thank you so much. I really appreciate you guys coming out here.
Yes.